Hi there, students. Welcome to class. Welcome back to learning about parallel lines and transversals. And remember in the last lesson that we just wrapped up, oh, by the way, this is Mrs. Brunk. In the last lesson we just wrapped up, we learned about how we can tell some things about our special angle pairs, the corresponding angles, the alternate interior angles, the alternate exterior angles, and the same side interior angles. We can tell some things about the relationship between their measures if we know that the lines that form them are parallel lines cut by a transversal. And today, this lesson is going to sound very similar to the last one because we're actually going to learn the converse theorems. So that word converse sounds like reverse, and in fact that's pretty much what a converse statement is. It's actually a statement that takes a conditional statement like if P then Q, or if two lines are parallel and cut by a transversal, then the corresponding angles are equal, and it reverses them. So it would say something like, if two lines cut by a transversal form corresponding angles that are equal, then the lines must be parallel. So we're going to be looking at the converse or the reverse of these statements. Now, not every theorem or postulate that is obviously true, as it's a theorem or postulate, has a true converse. Sometimes when you switch around the statements, the two parts of the statement, change the premise, in other words, you change the truth of the statement. Like, for instance, if two lines form a linear pair, then they're supplementary. That is true, but if that's the linear pair theorem. But if you reverse it, if two angles are supplementary, then they form a linear pair. No, that's not necessarily true. You could have two angles that are completely separate, don't even touch, but they add up to 180. They can still be supplementary without being a linear pair. So we can't always just assume that a converse of a statement is true. It actually has to be proven. But it does turn out that all the theorems we learned in the last lesson, so remember these theorems right here, these ones, some of them like same side interiors postulate and alternate interior angles theorem, those actually have true converses. So that's what we're going to be looking at applying today. And those converse theorems are used to prove lines parallel. So let's say we start off with, we don't know that the lines are parallel as we did in the last lesson. We know just something about these angle pairs. And if we do, then we can make some statement, some conclusion about the lines that form them. So again, a converse is, a converse is a statement in which you take the conditional statement and switch the premise. And so here's the first converse statement, which I like to abbreviate it as the CONV and then SSI, postulate. So it's the converse of the same side interior angles postulate. And this one says, if two lines are cut by a transversal so that a pair of same side interior angles are supplementary, then the lines must be parallel. So if we get these angles and we find out that the same side interiors, like these that I'm highlighting right here, this one, this one, and this one, if we find out they add up to 180 degrees, then we know that the lines have to be parallel. So we meet the premise. If they're supplementary and they're same side interiors, then we can conclude the lines must be parallel. Now the next one is the converse of the alternate interior angles theorem. And again, a little abbreviation. So when we state these, converse of AIA theorem. And, And this one says, if two lines are cut by a transversal so that any pair of alternate interior angles are congruent, so if any pair of alternate interior angles are congruent, then the lines have to be parallel. So our hypothesis is we've got a pair of alternate interior angles that are congruent in measure, then the conclusion is that the lines have to be parallel. And again, if you kind of think about the drawing, what that would look like. If we were saying a pair of alternate interiors, so like this angle right there and this angle right here, were the same measure. I mean, if you think about just spatially how that works, if those angles are the same, those lines must be cutting that one transversal at the exact same angle, and two lines running at the same angle are parallel, because that's like implying that they have the same slope. And we know that lines that have the same slope are parallel from Algebra 1. and kind of from common sense. And then the final one we're going to look at is the converse of the corresponding angles theorem. And that one says if two lines are cut by a transversal so that any pair of corresponding angles are congruent, then the lines are parallel. So there again, you kind of think about a drawing. If you had corresponding angles, say like this angle and this angle are corresponding because they're on the same side of the transversal and the same position relative to the other line that forms them. So they're both in the same relative position. If those were equal, that means the lines would have to be coming into that transversal at the same angle. So that's another way to prove that lines are parallel. And there is one additional one, and I'll talk about that a little later in the lesson that we just didn't state in the lesson, but it's related to the other angle pair, the alternate exterior angles. So let's go ahead and take a look at some examples. So in our first example, we are going to find the angle measure that would make the lines parallel and then state the converse that proves lines parallel. So in other words, we're going to state the theorem, like one of the converse theorems that would say then the lines would have to be parallel. So if you look at in A, the angle that is labeled is this angle right here. And then they show a little question mark right in this spot right here. And they want to know what would this measure have to be? Oops. What would that measure have to be in order for these lines to be parallel? Well, in order for these lines to be parallel, that angle right here would have to be 65 degrees because that means that that would be a pair of alternate interior angles equal. And that was the criteria for this theorem. That's the converse of a, I guess I don't even have to do converse. I don't have to put the of in there. Converse of the AIA theorem. So if we can prove that these two alternate interior angles are equal in measure, then we can say that the lines are parallel by the converse of the AIA theorem. Now looking at B, they give this angle as 112, but then they want you to tell what would the measure of this angle have to be for the lines to be parallel. Well, remember, these are same side interior angles, right? So we want them to equal 180 degrees in order for those lines to be parallel. We don't want them to be equal. That's the one pair that's not supposed to be equal. They're supposed to be supplementary. And if they are equal, then it means another whole thing. It actually means the lines would be perpendicular to the transversal. But so we know that if this were 68 degrees, then these two would add up to 180. So by the converse of the SSI, same side interiors postulate, and again, I think it doesn't, postulate just means that this one was kind of the first one that they established because it was very obvious and the other ones were proven using that. I've seen different books use corresponding angles as the postulate and they build off of that. But in this particular one, see back here, they're calling that a postulate, converse of same side interiors postulate. Theorem means it's been proven using other properties. Postulate means it was assumed to be true. So, you know, most of these are pretty obvious things, but they chose one to be kind of like the building block, and then the rest of them were proven using it. So the next two, I want you to try as you try questions. So we're going to have you pause the video for a sec. Figure out the missing, or the angle with the question mark in it, that what it would have to be in terms of its measure so that the lines would be parallel, and then list the property that would then be used to support that lines are parallel. So please pause the video now, try C and D, and then tune back in to check your answers. Pause now. Okay, so for those lines to be parallel, for U and V to be parallel, in part C, the missing angle would have to be 61 degrees, because then 61 degrees plus 119 degrees would make 180 degrees. And then by the converse of the same side interiors, the lines would have to be parallel. Now, if the missing angle with the question mark there was 52 degrees in D, that would make those be congruent corresponding angles, and therefore by the converse of the corresponding angle theorem, the lines would have to be parallel. Now, a lot of times students will ask, do we have to write the converse part? Can we just say corresponding angles? And the answer is yes, you absolutely have to put the converse part, and that's because they're two different theorems. Not all theorems are, or postulates, their converses are true. So, but in this case they are, and it's really its own standalone theorem. It's got to have its own name, and so the way we can distinguish it from the other direction is by saying it's the converse of that. So yeah, that's really important because the conclusion says lines are parallel, so if you're using it to support saying that lines are parallel, that would be the one you'd have to use. Okay, so let's move on, and we'll get a little more complicated with these, so just throwing in some variables and whatnot. But this time it says find the value of x that would make the lines parallel. State the converse that proves the lines are parallel. So the first thing I always want to do is look at where are the labels in these drawings and see if I can figure out what kind of angles they are. So these two angles are in the position where they're alternate interior angles, right? So I know right away the theorem I'd have to use to prove the lines are parallel is the converse of the AIA theorem. And so in order for me to use that, I'd have to show that those angles are the same, which means I'd have to find a value of x that would make that one angle 80 degrees. So that's what I'm going to say. I'm going to say these two angles, 8x plus 8 and 80 must be equal, because that's the premise of the theorem, that if the alternate interior angles are equal, then the lines would have to be parallel. And so all I have to do is solve this. I'm going to subtract 8 from both sides. That makes 8x equals 72. Divide by 8, and that means x must be 9. So the value of x that would make this so that the lines are parallel would be 9. So then when you plugged 9 into this expression right here, you'd get 80 degrees and you'd have alternate interior angles be congruent. Now with B, we have these two angles. Now remember, these are called same side interiors, right? They're same side. And so if these are same side interiors, in order for the lines to be parallel, the same side interiors would have to actually be supplementary, not equal. And you can clearly tell they're not equal. One's quite large, one's quite small. One's acute, one's obtuse. So if we use the converse of the SSI, and we wanted to find x, we'd have to say those two angles add up to 180. So we'd have to say 5x plus 10 plus 13x plus 8 equals 180. And then we can solve that equation. It's a little more complicated equation, but we can solve it by putting our like terms together, right? These are like terms. The x terms add up to, let's see, 18x. Oops. 18x. And then plus 18 equals 180. We're going to subtract 18 from both sides. That makes 18x equal to 162. And if I divide 162 by 18, I get x equals 9. Oh, so x equaled 9 again on this one. That's kind of a coincidence. So I've done the two things they asked me to do. I've stated the converse that proves the lines would be parallel. And I found the value of x that would make that be the case. So if I were to take 9, plug it in for x in those two expressions, so let's actually just check it. So if I plug it into this top one, 9 times 5 is 45, plus 5 is 55. And when I plug it into the bottom, 13 times 9 is 117, and 117 plus 8 is 125. And 125 and 155 makes 180. So it works. So at this point, we're going to try a couple you-try questions. So just to recall what the directions are. The directions are to figure out what the value of x would have to be to make the lines parallel, and then state the converse property, theorem, or postulate that would be used to support that lines were parallel. So again, you're going to be solving and writing some sort of equation. So look at the angles. Do the angles look like they are like the ones in the position to be corresponding or alternate interior? If so, those would have to be equal, and you'd use the corresponding theorem that goes with that converse theorem. Or if they look like they should have to be same side interiors, they would add up to 180. So try D and C, and then tune back in to see how you did. So please pause the video now. All right, thanks for giving those a try. In C, the value of x would have to be 6 to make those corresponding angles, right? They're in the corresponding or same relative position, both to the right of the transversal and below the other line, right? So that's called corresponding. And so we would be using the converse of the corresponding angles theorem. And then in D, those angles represent alternate interior angles, and if they were equal, the lines would be parallel according to the converse of the AIA. And a value of x being 4 would make it so that those angles are equal. All right, let's move on. Now actually, one thing to note, and I'm not sure why they don't include this theorem in here, but there's also a converse of an AEA. So let's say instead they had given me sort of like, I don't know, like this angle, like say in B, or like this one, and then this one. If we could prove those were equal, the lines would have to be parallel as well. And so just, that's another one to keep in mind, but the 3 that were stated earlier, we've seen examples of each here. But the converse of alternate exterior angles theorem is also a theorem. So example 3 says use the given angle relationship to decide whether the lines are parallel and explain your reasoning. So now we don't know. These lines just could be really close to being parallel, almost the exact same slope here or slant, but maybe they're not. And so we want to see if the evidence that is given in each part of the question is enough to support our claim that the lines are parallel. So they said that angle 3 and angle 5 are congruent, 3 and 5. Okay, well, what kind of angles are they a special angle pair? And in fact, they are. So I could say that the lines would have to be parallel. I could say L is parallel to M because, because, my stylus is acting up. Because angle 3 and angle 5 are alternate interior, are congruent alternate interior angles. And so the converse, let's see, so by the converse of the AIA, L is parallel to M. So there's a little explanation. This would be maybe like a sentence or paragraph proof instead of like a 2-column proof. We could have done this in, like a 2-column form, or really there's just a theorem. Honestly, the theorem is enough to say converse of the AIA says then the lines have to be parallel. So in B, they say, let me get rid of the markings. We're going to use the same drawing again. It says that the measure of angle 4 is x plus 20. So I'm going to label this x plus 20, and that the angle of measure of angle 8 is 2x plus 5. And then they tell me that x is 15. Okay, so these angles are in the position of corresponding angles, right? So if they were equal, we would be able to tell then for sure the lines would be parallel. But we don't know if they're equal yet. So what we have to do is we're going to take this 15 and we're going to plug them in to both expressions and find out what their measures are. So if I substitute in 15 in for x into measure 4, I'd say 15 plus 20, and that's 35 degrees. And then I could also plug it into angle B, so the measure of angle, or not B, but 8, and it would be 2 times 15 plus 5, which 2 times 15 is 30, plus 5 is 35, and so now we've got angles equal. We can say the measure of angle 4 is equal to the measure of angle 8, because we actually substituted those in, and we found out they are, and so then we can say, so by the converse of the corresponding angle or I guess it's a theorem in this book, then not M, but L is parallel to M. So with something like that, we can't assume that they're equal. We actually had to find out by substituting in 15, and if we had to put a reason, for that first line that we did, we could say like substitution. We actually substituted in I've seen sometimes people write these in like 2-column format. So they'd show the substituting into the expressions, and they'd use the support as substitution. And then they'd show that the angles are equal because they're the same measure, and then they could say the lines were parallel. So this is a little more like I said, a paragraph or sentence proof. 2-column format you could as well, but you'd have to include things like the substitution property to be able to show how you're putting 15 in for x. Okay, and our final example here. So it says, identify the type of angle pair described in the given condition. How do you know that the lines L and M are parallel? So the first thing first statement is that 3 and 6 add up to 180 degrees. So first I'll take a second, think about what kind of angle pair that must be. Okay, if you said they were same side interiors, you're right. So you could say angle 3 and angle 6 are same side interior angles, right? Same side interior angles. And since they're supplementary, then the lines, then L is parallel to M. And again, it's by the converse theorem, converse of same side interiors, which was a postulate, I guess. But so the reason is because the angles are supplementary, then the lines must be parallel by the converse of the same side interiors. So see if you can, as a you-try question, do the same thing with this next one. So it says angle 2 and 6 are congruent. What you need to do is establish what kind of angles those angles are. See if they meet one of the requirements for one of our theorems, and if so, you can say that the lines are parallel. So pause the video now and give the final example a try. All right, so thanks for giving that one a try. So angles 2 and 6 are corresponding angles, and since they're congruent, because see how they're corresponding, they're right there in that position, same relative position. So since they're congruent, L and M must be parallel by the converse of the corresponding angle theorem. And that does it for today's lesson, so thanks for coming to class. See ya.